All right. So who do we have on board so far? It is 6 o'clock straight up. Well, bad news is our guest speaker has flaked on me. So we're going to have to hit him with some really hard questions. I told him we would reschedule him for next week. So we'll go ahead and do that. If you guys don't want to have your video on, that's fine. I do love seeing the smiling faces and at least an occasional smirk when I crack a joke. You know, a pity laugh now and then helps. It's up to you guys. So with that being said, I'm going to dive in. We'll get as far as we go tonight. We're a little bit behind in terms of the overall schedule where we should be. And so we're going to start introducing the next lesson before we finish this one. So you'll have the intro to earthwork and volumes, but next week's quiz will be on topography, which is what we're going to mainly cover tonight. We're just going to have a little bit of overlap. We won't have a nice clean break between topics. Thank you, PG&E. But tonight, Monday, November 9th, class number 9. What is our agenda? I'm going to talk about exam number 2. You guys may or may not like what I have to say about it. Talk about topography and how do we come up with topo maps? What do we do? How do we generate the information? And then we're going to talk about volumes and earthworks, just very briefly, kind of like a real live scenario, a little case study, sort of, so to speak, just to get an introduction on it. What I would like to do for exam 2, I wish more people were logged in. I don't know what happened, where everybody went. But in terms of exam 2, scores were across the board. After exam 1, Marcine had pointed out that oftentimes instructors will let you redo the exam for partial credit. So I came up with a little bit of it's up to you, totally at your discretion. You can rework the entire exam, which has been posted under assignments, under extra credit. So you're welcome to join in that way. Let's see. I click on chat and it goes away. Don't get it. Oh, hiding behind the hand, behind it. So show all of your work. Use engineering paper. This needs to be the neatest, tidiest submission yet. Here's the catch. It is only available for 50% of the points that you missed. So for example, if you got a 73 on the exam, the difference between that and a perfect score is only 27. It's 27 divided by 2. You can only max out at 13.5 points. So you have to decide whether or not it is worth your time and effort to go back and redo the entire assignment. If you got a 90 on the exam, the most points you're going to be able to get are 5 points. If you got a 45 on the exam, I would seriously consider redoing the exam, going over it. The due date for this will be Wednesday, November 11th at 2:30. So those of you that are familiar with my office hours end at 2:30. So that should give you a very good hint there, okay? So up to you. It's an extra credit. Again, apologies about homework number 7. You do have to hit the publish button when you're done. You don't just hit save and go on about your merry little way. So that is now posted. I've given you till the end of the week. No kidding. It is 5 questions. Very straightforward. If you have any questions about what's on there, come by at office hours, send me an email. I'll get back to you there, okay? Any questions on that? Does that sound fair? Okay. I see, now I get a head nod. I like that. All right. Thank you, John. Okay. So that's the deal for exam number 2. What's next? All right. Now we're going to talk about topography. And this one, it looks a little bit blurry. I'm just kind of looking here. We've got some gravel. I just look for keywords when I first pull up a document of any sort. What are the keywords? All right, well, you know, we've got some shading that's indicated. We've got some icons here. But basically, this is going to be one of our pretty typical topo maps. All right. Let me get down here. So we can see that we get a lot of information from this. Looking at the spacing between the contour lines tells us a lot of information. The other figures and locations, key points that are on this program. All right, Kenny's joined us. I love the icon. That's great. Okay. What it does is once you're familiar with reading topo maps, once you get comfortable with that, you start to figure out, you start seeing these things in 3 dimensions. It just kind of starts happening based on the spacing. We see we've got a relatively flat space here. We've got some steeper areas here. Are they going up? Are they going down? We haven't dug in yet. We don't know for sure. You know, access items, where are our drains? What are our points of interest on these? So there's a lot of information that we put out on construction drawings. All right.
So I just have a quick question. I keep happening to notice that there's shading sometimes underneath on the map. So does that convey anything?
It can. It definitely can. We'll look at a variety of maps. If you have one particular in mind that comes to mind, let me know. Let's try and bring it up, and we'll talk about that one on the screen.
Okay.
Talking about visual concepts, it's really hard to do this 2-dimensionally, right? But this is ultimately what we're doing. We are taking an existing structure, an existing geographical formation, whether it is a parcel, whether it is a mountainside, whatever, right? We're taking it, we're slicing it into these pieces, kind of like a layer cake or a tiered cake, right? Cutting it into pieces every 100 feet. We're going up and cutting off another slice and saying, what's the area right there? Where is that spot? And then by compressing it into 2 dimensions, that's what we get when we get, so we get a topo map, we get our topography, okay? As we looked at last week, I don't have any notes on my slides for some reason this week. We started out looking at this one at the end of last week's class session, okay? What information are we getting from this? What do we see? Looking up above, it's pretty easy to see. Yeah, we've got a hillside, we've got a kind of a gradual slope, we've got a steeper slope. Over here, on the other hand, you know, some little depressions, where some rivulets come down, where the runoff is. Looks like there's a drainage piece here. Looks like this might be a water formation, a lake or an ocean, something along those lines. But then to get the scale of it, we come down to the topo map to give us more of that detail. How steep is that? How tall is that hillside really? Well, we can kind of look here and see, all right, well, we've got a contour at about 260 feet, but when we come down here to the bottom, we're only at 20, 40, 10, probably, down to 0, down to our lake level or our ocean level. So that's a pretty substantial hill. That's a 260-foot hill. Lots of information that we can glean from all of these different parts and pieces, okay? And that's what we're looking to capture with topography and contour lines. What are the big changes in elevation? How do we tell a 2-dimensional story, or sorry, how do we tell a 3-dimensional story in 2 dimensions? Okay. All right. Contour lines, they will always connect points of equal elevation. Contour lines will never cross each other. You will have major and minor contours. Major contours, if you have to take anything out, you take out the ones in between, but you've got to have those big bold points so you have your frame of reference. Not every topo line will have to be numbered. You won't have to put a call out on every single line, but you do need to capture the big points, right? There might be a point elevation that's worth noting, depending on the scale of your mapping. Okay? And we want to know features of interest. Do we have a depression? Do we have an outcropping? What are we looking at? Is it a hill? Is it a slope? What do we have going on? Is it a depression? All right. So, little grainy, but this example is how we would expect to see typical contour lines. Okay. We're fortunate here. They're marked. Every one of them is marked, so you don't have to guess at which direction you're going. The X marks that peak, or it could mark the depression if these contours were going in a different direction, right? If these were dropping in value, we might mark the very bottom of our depression. Here we want to note the high point on the hill. You would want to label that top elevation as best as you can. Okay. Is it 290? Is it 299? 295? It might make a difference. We might need to know that. But we can also see that that high point, where it's located, it's not dead center of that contour. So that tells us a little bit of something too. It tells us where it is. It tells us that we're sloping off low left and coming up to our peak on the upper right. Okay. If we follow these contours down the hill, we see this dotted and dashed line in between. Now, what I said was contours never cross each other. But what this is showing is that that is a depression. That is a little bit of a valley. That's what's going on there. Okay. So there is some kind of feature there that's showing us something's happening. It's actually a low point because as we cross that, we come back to 250. It could just be pretty flat, but a slight drainage swale. We come to 260 again, but as we keep going, it's pretty flat here, 260 to 260. That's flat, right? Then it starts dropping pretty steeply, 250, 240. Now these little lines, those are called hatchers. And what they do is they indicate the direction of slope downward. Okay, so here's our little X again. That's going to be our lowest point, our drainage point. But we can see that we're dropping in slope down to that low point. Okay, down to that little inlet. Any questions so far? All right. Creating a topo map. So what do we need to do? If we have a bunch of points, how do we determine where the contours go? And this is going to be part of your homework. So what we want to look at, most of the time we get spot elevations, right? The setups and the systems that we've been using, we've been talking about, your labs have all been point elevations, right? If we were to go out with a GPS unit and a monitor and a sensor, and we could get every 6 inches and get a type of map that way, we can get more consistent points. But here we get a scattering of a handful of points, all varying. So if we were to look at this particular map, we have our traverse. That's just our control point. That's where we started. We gathered the information from all of these points. We got the elevations. We'll talk about how those are generated in a little bit. Yeah, breakout rooms aren't going to work with 5 people, but okay, we'll figure it out. So now that we have these points, looking at those points, assume north is straight up. What could you tell me about the terrain that we're looking at? What's going on geographically?
It's sloping down toward the bottom part of the screen.
Okay, so it's going down this way. It's sloping towards the south, we'll say.
Mm-hmm.
What else? East or west? Can't really tell.
Kind of the same.
Yeah.
There is a depression, I think. No, never mind. It's pretty consistently going down towards south, I think.
Yeah, so here's my lowest point. Okay, where's my highest point? Right here. So if we wanted, we could say, yeah, I can determine the slope of this plane, of this site, right? We could take our highest elevation, subtract our lowest elevation, and come up with the slope. But there's a little bit more happening there. That's not going to give us the most accurate answer. So now we need to do a little bit more of some interpolation, so to speak. If I switch over, you guys are seeing the whiteboard now?
Yes.
Okay, great. All right, so I'm going to switch to pen mode. Let's go green. I'm feeling green today. So what we would want to do is we want to look at these points and we want to figure out somewhere in between them, where are our major and our minor contour points going to go? Where do our lines need to fit? Whole numbers every 5, 10, 20, 100 feet, 50 feet. How do we know what our scale needs to be for our topo? Okay, so we need to figure out where to draw the lines and how many lines to draw. Which lines do we need to draw? So because we've only got a handful of points and we don't range too far, we're within 10 feet, I don't really want to do 10-foot contours. That's not going to give me a whole great amount of data. If we say 5 feet, that gives us a little bit better, but not as detailed. If we say every single foot, we could probably get something fudged in, right? We can get it worked in. How do we go about doing that? Well, we would want to look for our points that give us those indicators already. Points of known elevation where we can say, hey, that's great, we're already at 458. So if we were to continue to draw a line for those points, where do we want that to go? Well, I can see that somewhere between 58.9 and 57.7 is going to be my 58. Not quite midway. And again, this is just going to be roughing it in so we kind of get the feel for it, but you know that there's going to be super exact, precise ways of doing the math and getting that line in there. We could take the distance between the two, we could take the change in elevation, and we can come up with where that point would lie, right? We're going to ballpark it today. So I'm just going to take my pen and I'm going to say, you know, kind of in between here, maybe a little bit closer, right? So whole foot, 3/10 of a foot, about right there. My green line doesn't show up, all right? So we'll plot a rough point there. So I know that my 458 has to come through this point, but we have 2 points here that we can interpolate between. So we have to go 1 2/10 along that way, along this line, imaginary line in between the two, and 9/10 backed off of it. So not quite halfway, a little bit closer to that 458.9 again, right? So I'm going to put a little dot there, just a little placeholder. Okay. So we come over here, we start working our way to the left, 459.2, 458.8. All right, so we know we need to be down in here somewhere in between 58.8 and 57.1. So 8/10 off of that one. About the same thing, about like that, right? Again, we're just roughing it in to get a feel for where these contours would go, right? how do you start reading this? So sticking with our 458 mark, right? 460.6, 458.8. Those points are pretty close together for being almost 2 feet elevation distance, right? Difference, sorry, not distance, difference. So not quite 2 feet, but we're still going to be down here a little closer to the 458.8. So we'll put a button right there. Oh, that's a big one. All right. And again, oh, no. How come you guys didn't stop me? I was on the wrong side of it.
I was going to say that something doesn't make sense, but sorry, again, wasn't sure.
I'm human too. We all make mistakes. So it would actually be down in here, probably a little closer. 57, 58-ish right there, maybe. All right. And then somewhere between 57.2 and 59, that's probably going to be pretty close to the middle. All right. So I have my little lines. Now, you guys have seen me draw lines. I can't draw a straight line to save my life. Let's see if we can kind of sketch in a curve using this technology, okay? So I kind of want to come in here, hit this green point, hit that green point. I have to come up and tag that 458. Oops. Okay. So this part's a little wonky, but you get the idea, right? So we've got one contour line in there kind of roughed in. So which way do you guys want to go? Should we go to 457? Should we jump to 454? What do you guys want to do next?
I'd like to go down to 457 and just see how that works with the other contour line that we already created.
Okay, so I'll do another one in red. All right, 457. Well, here's 457.1. So I would say if this is 455.2, we're going to be right about in this area between those 2 points, right? Similar here. So 7/10, 7/10, that's right in between. So we'll hit our 457 right there. 456.8, 458. So 1 and 1.2, that puts us a little bit closer to the 458. So we'll put our little dot right there. Now down here, 456.9, that's pretty damn close to 470. So we'll keep that pretty close. All right, 457.2, almost a whole foot in between those two. So we're still going to be pretty close to that 457.2. So we'll put the dot there. Okay. So here we'll start trying to connect these points. That was a little better. Okay. So now we're starting to see some a little bit finer detail emerge. This isn't just a big, nice sheet where everything's all at the same elevation. It's not all the same contours, right? It's not a nice flat plane from the side, right? We're starting to see that there's some undulations in it. There's some movement to it. All right, Othello called out 457. Who wants to pick the next one that we do?
We can go to 456 if we are going down.
Okay. I was going to say jump around. We can get some space going. That's fine.
Okay.
456. All right. So let's go blue pen for that. Here we have 455.2, 457.1. So 456 is going to be pretty much in the middle of those two. Pretty close, right? Maybe a little bit. We'll just kind of figure something in there. All right. So now we come to kind of a little bit of a quandary. We probably want to look at what we're doing between this 456.3 and these 3 points down here. That might tell us something a little bit. There might be a little more detail that we can pick up by looking at what's happening between those 4 points, those 3 points as it relates to that 1, right? So 452.2, 456.3, that's going to be right about midway, right? So we'll put a little bitty line there, just a dot. If we go 456.3 to 453.7, that's what, 2.5-ish, right? So we're definitely going to be much closer to this 456.3 from here, if we're looking at a 456 elevation, right? About like there, you think? Sure. Okay. So that's going to give us a little bit more detail, and we're a little bit further out. We still are going to be kind of in this ballpark. So if there were something weird happening there, we would hope it would stand out by looking at what's happening between those, along those different lines. Okay. We're basically just taking the cross section of this between these 2 points and saying what's happening in between there. Do we have that particular line of a whole number elevation that we can identify along that slope? 456.8, 455.5. So we're going to be just a little bit closer down here. Put the button there. About one whole point, one whole foot in between these two. So about midway probably. Okay. All right. And again, we're going to be pretty close to this 456.3 since the next one is 453. And if we look here, we're actually going to be, so there's 2/10 to 456, and there's 3/10 to this point. So again, we're going to be kind of right in the middle. So how many of you have done graphs with Excel? Probably most of you, right? Okay. So you can smooth out the line. You can go and you can hit every single point, right? And you get this little jagged line. Or you can tell Excel, kind of interpolate for me. Make that a nice flowing line. That's what we're trying to do with these points. We're just trying to smooth them out, except we don't have Excel to do the graph for us. Okay. So let's connect these points coming in, sweeping. There we go. Rough and dirty. There. Yeah, okay. So again, my artistic skills are seriously lacking, but you get the idea. You guys want to do another one? Just giving you ideas on what we're doing.
Is it possible to do 453?
Well, it's not impossible, but let's do 453.
I think it's impossible. I think it is impossible with this set of points because we don't have more than one dot to connect it to, right? Or for,
that's right.
Yeah, just one. Sorry.
Since we just have the 1 point, if I take, let's just look at any 2 points. So if we look between this point here and this point 3.7, well, my little, let's go hot pink here. My dot's going to be right here, right? 456.3, 453, our elevation of 453, still right there. So right now, all we have is a point, and we know that things are headed that direction. That is our lowest point on our map, on our data set, okay? our highest point here at 462.9. Theoretically, we could, once we keep going, once we fill in all these other points, we might be able to somewhat correctly guess what might be happening one below or one above our last point. Let's do 461 and see what that gives us. See if anything pops out, because right now we're seeing this little ridge here, right? That little whoop-de-doo. So let's see if that continues or if it seems to flatten out. Ground never does what you expect it to. All right, so take the yellow pen now. Let's do 461. So there's a nice one. We've got our point. All right, put my little dot there. All right, 462.9 and 458. Why my brain just quit on me? 2 and 3. So we need to be about 2/3 of the way. 3. That's 2. About right there, you think? Sure, why not? All right. We're doing 461. 461.1 is going to be right about here. Pretty close to here. And then from 459 to 461.1, we're still going to be right about here. Okay. So we're able to get 4 points on this. The more points, the better. But we've got something to go off of, right? So I'll take that and say, nice little sweeping line. Starting to flatten out, it looks like. That little increase seems to be flattening out a bit. We might want to take 460 and see what happens in between. But here I would probably hazard a guess that 463 is probably going to do something like that. Nothing great, nothing earth-shattering, no major features there, but we could kind of interpolate something based on what we're seeing. Contour lines always come back to themselves, right? And it's a hard concept to fully grasp, because you're going, wait a second, we have lines that run off the page. Well, theoretically, that elevation doesn't go away, right? They're usually closed loops when we go out and we survey, because we're taking slices out of the earth. It might be a giant loop. It might be absolutely enormous. Whether it's on the page that loop closes, or whether it's off the page, off the map, it's still, that contour still exists, right? That line in space, it's a flat plane. And anytime you cut something, no matter what angle you cut it at, that cross section is always going to be a closed object, right? Any questions? You guys want to do another one of these? Another contour? Or does my chicken scratch scare everybody?
No, it looks good. I was just wondering, what's the significance of like the shape, this like polygon in the middle?
The polygon in the middle, that would be our traverse.
Okay.
So if we went out and had our setup and had our traverse to go back and find these points, that's just kind of like our control point. Does that answer your question? Is that what you were looking for?
Yeah.
Okay. Is that good? Moving on. One more. All right. Because this will be your homework. All right. So back to the presentation. So Othello, I believe you asked about shading. And so what I wanted to point out was that there's an old school method. Instead of topo lines, what map makers would do is they would draw these little parallel lines to indicate the density of the slope. The steeper the slope, the darker the lines, the more hatched they were, right? So that's what we're looking at here is a sample of that. We don't have any data points, but we can definitely see that we've got a hillside where the steeper portions of our slope occur, where the more gradual portions are, and where the highs and lows would be, okay? So even without any numbers whatsoever, we can still kind of identify what's going on. That's pretty much an obsolete way of doing it. But when you look at a map that's got that on there and you realize that all that is lines, and it still tells a pretty impressive story. Okay. It'll still give you a lot of detail. All right, next up, we've got an example problem. We have a contour map. Interval of 10 feet, a scale of 1 to 2,400. I really got to put the comma in there. All right. If that measurement there is 3/4 of an inch, what's the average slope between those points? You knew slope was going to come back to bite you in the butt, right? That's why we kept going over it and kept going over it. Slope percentage, slope ratios. How do we define what's happening to that piece of land? So what are our knowns? What do we have? The change in horizontal elevation. That's what topo lines are. That's what our contours are. Horizontal elevation above a datum, right? The change in elevation is 10 feet as defined by our contours. We know what our scale is, and thanks to that handy dandy chart that we had from last week, we also know that that's equivalent to 1 inch equals 200 feet. We know what our change in horizontal is. We measured it 3/4 of an inch. So how do we find the slope? My dogs are going nuts. All right, so our change in elevation, our change in horizontal position, our distance between those 2 points, converting that using our scale, 3/4 of an inch. If 1 inch equals 200 feet, then 3/4 equals 150 feet. The formula for our slope is delta V divided by delta H multiplied by 100. So our 10-foot change in vertical elevation divided by our horizontal change in elevation of 150 feet, divide that by 100. That gives us our slope of 6.67%. Okay, it's not an angle of 6.67. It's a slope, it's an angle. Oh God. It's a percentage, okay? So we're saying that for every 100 feet you go horizontally, you will rise up 6.67 feet. That's what that is telling us. From that, we can then take the inverse tangent and come up with what the angle is. But right now, when you're given a slope like that, it really is just your horizontal and your vertical differences. Okay. That's mostly what we would be doing with these kinds of problems, these kinds of contours. What's the slope between this? If you measure from here to here, what's the change in vertical elevation? Okay. Little word problems that we would end up getting into. Topo maps and topography maps, they can be large, medium, and small scale. Now, this is where it's going to be a little bit confusing, all right? So let me get to my notes here on this particular one. A small scale. A scale is considered small if it is 1 inch equals 1,000 feet or more. Right. So here we have a scale of theoretically 1 inch equals 300 miles. That's a pretty big area though, but it really is a smaller scale, right? 1 inch equals a very large amount. The medium scale, anywhere between 100 feet and 1,000 feet. 1 inch equals 100 to 1 inch equals 1,000 is considered kind of medium. A large scale is considered 1 inch is 100 feet, which would be something along these lines. Okay. So we have our large scale here on the left, where we're zoomed in and seeing things that way, versus our small scale, which is when we're zoomed out. So the difficulty here is when you look at how you're looking at a much larger area, but the scale really is much smaller. Does that make sense? That one took me a little bit to kind of wrap my head around. Okay. So the three things you want to remember here: small scale, 1 inch equals 1,000 or more. Large scale, 1 inch equals 100 or less. And medium, right in the middle. Everything else. Okay. Generating topographical data. So far what we did, that first problem that we did, drawing in the contour lines. Somehow we've got to go out and get that data. This time we were given that information, those sets of points. Couple ways of going about it. There's a direct method and an indirect method. Direct method is I go out and I set up, I take my rod and I go and I look for those points that are exactly the topo the contour elevation that I'm looking for. So if I were standing on that hillside, right, the one we were looking at, 400 versus 450 something feet, and I wanted to go find that exact line, I could go out, set my rod, take my reading, and come up with an elevation of 457.7. Okay, well, if I'm trying to find 458, I know I've got to go up the hill a little bit more, but how much more? It really is the trial and error method, finding the direct elevation. It's very convenient. It's very, very easy to draw your topo lines off of that, because all you've ever recorded are your whole foot increments, right? Or your 10-foot increments when you've mapped those out. So you take your position, you take your direction, you locate that point in space. Now we're locating the elevation of it. Now we found that spot. Okay. Direct method, very rarely used anymore. It's too time consuming. It's too cumbersome. The indirect method, we just did the indirect method. Go out, get a scattering of points, and interpolate between them. You want to find those contours, you want to find those interesting features on your site. The highs, the lows, anything where your grade changes. Okay, you want to start capturing those particular points. Different indirect methods. The controlling point method, it's wherever your ground slope changes. So if you have a little bit of a hillside and it comes along kind of flat, and then it gets a little bit steeper and then it flattens out again, you want to hit those points where those contours have changed, where that slope has varied. Okay. Any change in slope. The cross-section method. You go and you stake across the cross-section of a roadway, typically used for long, linear kind of projects, right? Go and get your cross-section, and then we can figure out what's happening in between those. So you would map those at your stations. The grid method. So what we could have done is we could have divided up that drawing into different quadrants or different shapes. Okay? We could have gone in and done every 10 feet, we don't know what the scale was on that, so that's kind of hard to do. But if we knew what our scale was, we could go and overlay a grid on top of our site. We can average out each of the corners to find out what's the average elevation in that smaller area, or what would be the elevation in that smaller area. Try and figure that out, okay? Take the average, kind of like the corrections and the adjustments that we've been doing. Triangulation is what you guys will be doing in your lab. So that's the method that we're going to end up kind of going over a little bit. Let's see. All right, indirect methods. So we need to figure out how to determine the elevation of a point. Different scenarios. Where's our instrument, where's our benchmark, and where is our point that we want to know? Okay, when we have that, 6 different scenarios. Now, ideally, what I wanted to do tonight was you guys were all going to divide up into breakout groups, and we were going to go through, and each group was going to take a scenario and come up with what's the formula to find the elevation. What are we looking for? How do we find the elevation at point 1? Because these are the situations that we would be in out in the field. We'd have our instrument, we'd have a benchmark, and we'd have our readings. That's really it, right? So what we're going to do instead, I'm not going to do that. The evil gears in my mind were starting to spin. So we're not going to do, I was going to just say, all right, scenarios 2 through 6, that's your homework, go. We'll walk through scenario 1. We'll talk about it, and we'll see if you guys want to continue on that. All right, so for now, let's go look at scenario 1. All right, how do we find the elevation at point 1? What are our formulas? What's the math? All right. So we draw it out. HI is what? Okay, you're all going to have to chime in here.
Height of the instrument.
All right. Awesome. Okay. So we've got our elevations. RBM. What would that be? Logically, what do we think?
That'd be forward site benchmark.
Reading at benchmark.
Yes. Yeah, so that's going to be the reading at the benchmark. Okay. Actually, it's not the reading. It's the rod height. So the way this was set up, it's a little bit odd. So the rod at benchmark and the rod at point 1 are actually the same. Okay. V at our benchmark, that's going to be our change from the top of our rod down to our reading. V1 is the top of the rod down to the reading. And what we're trying to find is this elevation 1, okay? It was a little bit funky, but the math ends up working out, okay? So if that were the case, what would be the formula for finding elevation 1? Okay, so we have elevation 1. Well, what do we have first? We know our setup is plus the height of our instrument plus the reading at 1 minus the whole rod, right? Gives us this distance here down to this point. So that would give us our elevation at point 1. From the differential leveling, our elevation at our setup, we've got to go into and figure out what the benchmark, go from the benchmark, because that's our known point. Our elevation setup, we really don't even know yet. So we take our elevation from our benchmark, we add in our total rod height, subtract out that reading, subtract out the height of our instrument, and that gives us the elevation at our setup. Okay. So elevation 1 is our setup plus the height of our instrument plus V1, subtracting out R1. Okay. The next formula was the elevation at our setup is our benchmark plus our rod height, subtract out our reading, subtract out the height of the instrument, and that puts us down at our setup. 2 equations, 2 variables. We'll solve for the one we want, right? Which is going to be the elevation at point 1. So, substitution. Our elevation at 1 equals our elevation at setup, which is this here, right? So all I did was plug that in, plus the height of our instrument, our reading, minus the rod. If we consolidate that down a little bit, so all I did was redistribute my variables in that formula. So I still have my elevation at my benchmark because that's my known. I have my reading at my first point, at point 1, subtracting out my reading at my benchmark, add the height of the instrument, subtract the height of the instrument, add my reading at my benchmark, my rod at my benchmark, and subtract out my rod at point 1. And that's going to give us our elevation at point 1 is our benchmark plus our reading at 1 minus our reading at our benchmark. Okay. So that's the magic formula. What we were going to do was have breakout groups. We were going to go through and prove the formula. Now that we have 5 people, not going to work quite so well. I was really hoping to get the breakout groups going. But since we don't have that, do you want me to go through, we can walk through some of these other scenarios? Or do you want to take my word for it that the formula for the elevation at any point is the benchmark plus the reading at that point minus the reading at our benchmark? Whether our instrument is on the uphill side, our benchmark is in the middle, whether our instrument is in the middle and our benchmark is at one end and our point is at the other. If you want me to prove it, we can prove it. If you want to say, yeah, I'll accept it, we can do that too. What do you guys want to do?
There's some posts in the chat about doing one more and possibly number 4.
Why am I not seeing that? Thank you, Marcine. Wait, who did we lost somebody. Oh, John. John disappeared on us. All right. So scenario 4. Well, that sounds like fun. Let's grab scenario 4. And we'll just paste it on over in our whiteboard. Oops. Yeah, I'm one of those people, I don't clean off the whiteboard. All right, so scenario 4. All right. So do we need to draw the lines, or do we want to start with formulas? Let's draw some lines. Let's go ahead and do that. I'll use red so it stands out. So I have my height of instrument. So all my sites are going to be based off of that, right? All our readings. Let's see. I don't need to label everything here, but if I do this, oops. Why can't I get my text? There we go. All right, so our elevation, I'll just call it E1. We need our elevation at our benchmark. We have our readings at 1, our reading at our benchmark. What else do we have? We have our height of our instrument. And then we have the reading, sorry, the rod 1, rod benchmark, reading 1, reading benchmark. Okay. So let's put those in some semblance of order here. What we know is that our elevation at 1, we don't know the height of our instrument until we solve for it. So do we want to start with our elevation at 1? Do we want to start with our elevation at our benchmark and work backwards? Let's start with our benchmark. Okay. So our height of instrument is what? It's our elevation at our benchmark, going backwards, right? So if we follow the path, starting with the elevation at our benchmark, we have the rod, okay, speed, add the height of our rod, right? And here we would, hang on. We would subtract out our benchmark, the reading at our benchmark to get to this elevation, right? To get our height of instrument. You guys with me? Okay. So once we have our height of instrument, this one's a little bit tricky because if I use this drawing, reading the drawing, it's a little bit rough, right? So since we're dropping down, we want the elevation at our setup is going to be what? That's our height of our instrument. Is negative height of our instrument, because we have to drop down here. Actually, no. Sorry, okay. You had to pick number 4. So this elevation, sorry, at 1. Hang on, what the hell? Elevation at 1. So we have to go up the distance of the rod, we have to subtract out our reading. And then subtract out you guys are leaving me hanging here. It's not right either. Here's what we're going to do. Elevation at 1 is our elevation at our setup plus the height of the instrument minus the rod height. And this is showing that we've got a negative reading here. So we're going to subtract out a negative value for our reading at 0.1. Okay. What's the elevation at our setup? So where we have our instrument, right? It's our elevation at our benchmark plus the rod minus the reading at our elevation, our benchmark, minus the height of the instrument. So the elevation at our benchmark plus the rod minus our reading minus the height of the instrument. Just following that line and subtracting it out. But our elevation at 0.1 is the elevation of our setup plus the height of the instrument, subtracting out the height of the rod and subtracting out the negative reading at that point. So we'll do our substitution. Our elevation at 1 is this, the elevation at our setup, right? Plus the remainder of that equation. I'm going to copy this. Down on this next line. So let's do a little reorganizing. So subtracting out a negative turns that into a positive. We're adding the height of our rod. We're subtracting the height of our rod. So those two will end up canceling each other out. So we'll put those two together. We're subtracting the height of our instrument, but we're also adding the height of our instrument. So those two cancel. We're adding our reading at 0.1. Oops, got an extra plus sign in there. So these last two pieces drop out, which gives us that our elevation at 1 is our elevation at our benchmark minus the reading at our benchmark plus the reading at our point. If we go back to the PowerPoint, the elevation of our point is the elevation, where's my mouse, of the benchmark, plus the elevation of our reading, plus our reading at our desired point, minus our benchmark. If I do it that way, that's the formula we came up with. Okay. Making sense?
For the most part, yeah. I just need clarification. I forgot to write down. What does R1 or just the R stand for again?
The R is the rod height.
Okay. Got it.
Okay. So what I will do is grab a screenshot of scenario 4. I will save a copy of that, and we can get that posted as well. Okay. So just like differential leveling, that's really all this is. You take your known point and work your way across. What do I see and what am I reading? What are my verticals? And how do I get back to the point that I'm interested in? All right, let's take a little bit of a break. 7:08. Let's come back at 7:20. I'm going to back up because we're going to do some more examples. All right. Oh, hell. So here's something interesting. If you don't open up the window, then you can't see that everybody's here tonight. So I think what we will do is the breakout rooms when we come back.
Sarah, did you publish the example for scenario 4?
No, I have not published that yet.
Okay.
Do you want that published? Let's see if I can do a dual screen.
I think that would be helpful for them, so they can look at the example if necessary.
All right, let me shrink this down. All right, I'll get that. Can you guys can they still see it if they're in a breakout room?
No, they'll only be able to see what's, and also as a heads up, the recording won't record anything in the breakout rooms.
Okay. So then what's the best way to do that? All right, let's see if that worked. John's all by himself.
I didn't copy the scenario.
What's that? Oh, all right. So let me copy those and paste them to everybody's room. Lesson learned. This is cool. All right.
He's asking if you can get another invite to breakout room 6.
Who is?
Kenny.
Kenny?
Yeah.
Kenny, I show one of your logins is already there. How do I? Can't get in there.
I believe there's also an option where you can give people the ability to jump from breakout room to breakout room if you want to do that too.
That's what I'm trying to figure out. I'm not seeing.
Have you updated your Zoom recently?
No.
That's, yeah, I a few days ago in class, I wasn't able to do that. It's in one of the newer updates.
Yeah, it's not giving me any options on the breakout rooms because they're in progress.
Oh yeah, that might be the issue as well.
Yeah, this is dumb. Kenny, stick with me. I'll get you there. All right. Did that work, Kenny? All right, Othella's the only one in 5. So I'm going to move you to 5, Marcine.
Okay.
Thanks.
Kenny's also asking if groups are working on the same number as their room.
Yes. Yes, you are. All right, back to recording. So now we're official again. So how did it go? Were you able to follow the ups and downs and the pluses and minuses and get back to joining, finding the elevation at 0.1?
More or less.
All right, well, that's a huge start. That's a good plus. Let me make sure I'm sharing my screen here. All right. I hope if I just close the rooms, then everybody comes back. So. Okay. Everybody has been given 60 seconds to leave. Awesome. All right, so what did you guys think of breakout rooms? Helpful, hurtful? Do we need better technology to make them work more effectively? That's probably a given, but.
It was kind of hard because we could only see each other, but we couldn't see the task at hand, so.
Okay, yeah. All right, so we will work on that for future endeavors, make sure that everybody gets what they need. I'm gonna move the chat to another corner.
I was just a little confused because I was in the breakout room by myself. So
you were all alone. Well, we lost somebody. Who disappeared on us? Anil left us. He was supposed to be in there helping you. All right. So did everybody manage to get to the cancellation of the height of the instrument and the height of the rod? Yeah. Okay. I like the head nodding. It works. All right. So what we have next is just kind of an introduction to earthwork and volumes. So we're going to talk about why do we need this information? What are we going to do with it? So far, what we've done is we've looked at the mathematics behind everything that we've been doing, right? Starting the semester, we talked about trig, about geometry, and we looked at angles. How do we analyze angles? Then we talked about different nomenclature for slopes. Rise over run, using a percentage for slopes, using an angle to describe that, whether it is a horizontal angle in a horizontal plane, whether it's a vertical measurement in terms of angular distance, angular direction. We talked about directions, right? In order to find any point in space, we need to know which direction it is and how far to go, right? So we covered horizontal angles, vertical angles. How do we adjust all of the above, right? How do we make sure we're looking at the right information? So kind of reiterating what our different situations were with differential leveling, we talked about how do we find the elevations at a given point, right? Given what we know, given the tools at hand, how do we find those elevations? We know how to locate those points, how to reference those points. Now we know how to find the elevation of them. That's going to give us that third dimension, right? So we've got length, that's our distance, our width, what angle are we rotating through? How broad an area are we covering? And now we've got the vertical component as well to give us that volume. Why do we need to figure that out? Initially, when we go out and we do a topographic survey or, plot out an area, we're looking at a piece of land. So we want to be able to create a map. We need to know where we are, what we're doing, what is there to begin with. Primarily what we're doing is we're determining existing conditions. Different scenarios come up throughout the engineering world. What information do we need? Why do we need it, right? We have an owner who has come to us and said, I have this parcel of land. I want to build a McMansion on it. I want a swimming pool, I want a guest house, I want a riding arena, I need a barn, yada, yada, right? So as engineers, as on the civil side, we need to go and figure out how do we make this so that the house is not in the middle of all of this chaos and that the outsides of the property don't drain right into the house. That would kind of suck, right? If we have to dig a hole for our swimming pool, do we want to put it at the highest point or do we want to put it at a lower point? Lots of different design considerations, but we need to know what we're working with first. What are our existing conditions? Then we can design. Then we come up with our proposed elevations. So that's where the earthwork and the volumes start to come into play, is once we know what we want to do with the property, what we want to do with the area, how do we make that work? How do we make that happen? All right, so we're not ready for the recap yet, but what I'm going to do is I'm going to switch gears and we're going to do just kind of a little case study description. All right, so true story. I'll try not to embellish it too much and I'll try not to spit venom when I talk about my client on this particular project. This is Google Earth Maps. We're in a little town called Rockland. It's just north of Sacramento. I don't know if anybody's familiar with where the area is. You can kind of see here, I hope you're seeing my screen. Google Earth, we're looking right up Highway 65, paralleling it. We've got an existing building here. We're looking at Cyber Court and Industrial Avenue. And we've been told that there's this parcel here that Verizon Wireless wants to build a data center. All right, sure. This is what's existing. Can't tell a whole heck of a lot. You can see a little bit of stuff, a little bit of features, a little bit of perimeter. You can kind of get a rough idea of what we're looking at here. All right, so that would be one of our first steps. What do we have? What's existing? On the construction side, typically, and I just say typically because I can't say always, we are given a set of plans, something to go and analyze, something to review. What do you want us to do? We're just the dumb dirt monkeys. We don't get to think for ourselves. The engineers tell us what to do, and that's what we go do, okay? Unfortunately, it doesn't always work out to where the engineers have everybody's best interest at heart or the right information at all times. So when we start out, and I'll zoom out a little bit so you can see the full plan sheet. If it will redraw itself for me. I hate this feature of my Bluebeam is stupid. Locking up on me. Yay. I love it when it does that. All right. So at 135 Cyber Court, Verizon Wireless Rockland wants to build a data center. Proposed 2-story data center. It says it's about 118,000 square feet. So that's pretty substantial. That's about 2.5 acres, roughly. We have an existing facility on one side. We see that we have an existing street. Looks like there's going to be some improvements there. Typical plan set is what we'd be looking at here. We have an index of what sheets are included in the plan set. What is our vicinity map? What's our overview? Our key map. And notice we have, even that is to scale. So if I needed to come out and take some quick dimensions, if I needed to rough in a number, I have a map, I have a scale, okay? Enlarging and reducing this, I'm not seeing anything that tells me where that I've got stationing, so I don't know that I could really use that scale to full effect, right? As I zoom in and zoom out, 1 inch changes how big it's gonna be. So something to watch out for with scales, which we've covered. Gives us some perimeters. What are our neighbors doing? Who's our architect? Who's our owner? Who's our engineer? Has it been approved? You can't do anything without county, city, local jurisdiction approval. The engineer, the architect, who's the electrician on the job, all of that information. Who do we contact for utility information? We don't know. There might be a 12 kilovolt utility line running right underneath this site. Or, as they pointed out when we went and toured the existing facility, there could be a fiber optic line that would shut down the West Coast for all Verizon infrastructure if we hit it. Well, we're the dirt people. We go out, we dig. Stuff gets in the way. Where is your line? We don't know. All right, so this is going to be fun. Anyway, first sheet, this gives you kind of an overview, gives you a legend of what those symbols, what the details are, what the abbreviations are going to be. Page 2, more of the same. more details, more notes, which you would see if my computer would work. I don't know why it does that. Okay, bear with me. Let's see, am I recording? Of course. Come on. See if this works. All right, so basically it goes through a lot of notes, a lot of details about what are the specifications, kind of a quick overview of what are the details for the storm drain. What do we need to know about the sewer systems? What do we need to know about the water lines? What's expected of us? What agencies' details do we need to follow? Who are we contracted with? Those sorts of things. A lot of that comes up. I don't know why this is doing this. Not cooperating, of course. Stupid thing. All right, so we've been asked to go take a look at this site. We've been asked to bid on the job. We can go to Google Earth and we can get a quick overview of, all right, well, we see where the site is. We see maybe a little bit of details. Let me go back to Google Earth and we'll take a look at that. All right, so we figured out that basically this is the site here, okay, this empty area. This is a PG&E facility. This is the existing Verizon Center. So if I zoom in a little bit, there's going to be things that I want to look for. Somebody went out and did a topo map of this. And if my Bluebeam were working better, I would be able to show you that. But even from Google Earth, there's certain things that we can kind of pick out. Anybody see anything that stands out? Kind of like,
yeah, I see that
the snowman is missing his nose.
Yeah, I see like remnants of a road in the area, or what it looks like to be.
This piece here?
Yeah.
Okay.
I also see that just faintly, but you can see like divots, I guess you can mention, in the ground, and it looks like it's sloping down to the right as well.
So are you talking about these?
Mm-hmm. Yeah.
Okay. So with practice and with experience, if you look at stuff like this, you can kind of see that it's little piles. And if you zoom out quite a bit, you can see that there are subdivisions all over the place, right? So, and where there are subdivisions, and especially up in this area where it gets really, really hot during the summer, you're going to have really a lot of swimming pools. And swimming pools generate excess dirt because we have to make a hole in the ground. So a lot of times what happens is project sites, when you get out there, somebody's been dumping swimming pools, the holes, all the dirt that comes out of them has been going to this site. Somebody's been dumping here. That means we have no idea what's underneath it. We have no idea what's in the middle of it. Maybe it's concrete rubble. Maybe there's some bodies. You have no idea, but you know that that is a warning sign when you get ready to go out and assess a site. All right.
Got it. That makes sense. Thank you. It's good to know, actually.
Well, really... and this little road tells me that somebody put some time and effort into creating this as a dump site, right? There's been no compaction. And if you try and put your hand, think about like a bean bag, and you push on a bean bag, it just kind of melts under your hands because there's no compaction there. Right. There's no restriction. We don't have any density in the material. And that's what we need to look for. We don't want to build a building on, well, welcome to Santa Cruz. We don't want to build a building on liquefiable sands, because then in 1989, you get a 7.0 earthquake and all of downtown falls down. All right, Othello, no offense, but somebody else, what else do you see?
Hey, Kenny, I think you're speaking, but we can't hear you. Or I can't hear you at least.
No.
It looks like there might
There's
be a
two
remnant
Kennys.
of the building in the lower left-hand corner of the lot. Up a little bit further. And to your right, just down a little bit. And then now right. There's a pile of rubble or something right there.
Yep. Yeah. So there's a pile of debris. All right. Well, who's going to be responsible for getting rid of that? Questions that we're looking for when we first start analyzing a site. Because, you know, like now we're waiting on the engineer to get us drawings. So even if we were the engineer on the project, these are our beginning conditions. We need to figure out what do we do to build this site to give our client what they want, which is a 2.5 acre data center. Some other things to note, any different colors, any colors that stand out?
Yeah, it looks like there's a trench that parallels the left-hand side and the top side of the property, which kind of looks like it might flood in the wintertime. So there might be a drainage issue. It's so flat there.
So some of the indicators, can you tell where the water's coming from and where it's going to? A guess.
Off the neighboring property.
Yeah, it looks like it's coming from the parking lot. You can see how it's miscolored, so it means that the water may be collecting there and then running off over to the other street all the way down there. Okay.
To a little drainage opening, a culvert pipe over here. So what I see through years of doing this is this gray area. I'm going to guess that with a ditch like this coming around the side, still a little bit of green when everything else is kind of brownish and dried out, then over here, seeing how much it's you can see it's a deeper depression towards the bottom. We're most likely looking at a drainage swale where there is a rock outfall to prevent erosion, soil erosion. Then the drainage ditch comes around the perimeter into an outfall here. Because if we zoom out a little bit more, there's a little bit of a waterway here. Okay, so that's telling me that's going to be a lower spot where everything is going to be draining to, just naturally. The other thing we can kind of get from Google Earth is down here in the lower right-hand corner. It tells you what the elevation is wherever your mouse is, wherever your cursor goes. So if I start out down here along the road, I'm about 129, 130 elevation. If I jump up here, I'm at 132, 133, 134. So my property is sloping from this back line towards Cyber Court. Okay, so that tells me that I've got a little bit of an angle there. I can identify that. Here's the catch. What's my elevation if I'm up on that paving area? So in this very short little distance, just in the width of this hand, right? I go from 134 to 138. So there's a big jump instead of from 134, a 4-foot jump over this whole distance, or a 4-foot jump over this little distance. What's that telling me? Okay, got a very, very steep slope right here. And that also tells me that all the water coming off of that site is probably going to flow towards this parcel, this property. All right, so let me see if I can get, oh, there we go. Damn it, come on. Let's see, this is, if it would render quickly, of course it won't. All right, this is the erosion and sediment control plan. I'm not concerned about that just yet. Oh, come on. Come on. Where did I get that? All right. It's locked up on me now. I broke it. All right. Okay. So specification notes. Intent, even details about the striping. What do they expect? What do they want from us, right? Legal description. Portion of lot 1, beginning at the northwest corner of said lot 1, thence along the boundary, northern boundary, meets and bounds. There it is. Plus, there's an assessor's parcel number. So if we need to go look up the property lines or the limits, we can find that. But it does give us that legal description of how do we define this property, okay? Parcel 2, portion of lot, blah, blah, blah. Trying to be very careful. Surveyor's notes. Basis of bearings. What are my reference points? What are my knowns? Okay, where are my benchmarks? What do I have? What can I work off of? And then surveyor's controls. Who did the surveying? When did it happen? Conventional surveying methods, dimensions are based on field measurements. We don't know who owns the walls. We're throwing out our disclaimer there, okay? No signs of earth movement, building, or construction, right? We see all the piles. We see the roadway that goes around there. Well, all right. To the best of my knowledge, at the time that I viewed the site, there wasn't a problem. Okay. Not located in a wetlands area. You're going to run into that really a lot, especially in California, where the environmental controls are so stringent. Okay, there's certain areas, there's endangered species that you have to watch out for. There are environmentally sensitive areas, there's protected areas. Places where you can and cannot work during certain months. So knowing what those requirements are, for example, going back to the Google Earth map, we saw that kind of waterway to the south of the property. That's something to watch out for. If we've got runoff, are we going to get in trouble for it? Yeah. If it ends up contaminating a waterway. 53/100ths gap shown to be corrected by future lot merger. Okay, so what that's telling me is that something didn't line up. We have 53/100ths error of closure between two parcels. So that's giving us a heads up, right? And then the certification of the surveyor. All right. Let's see if that'll work. Come on. Work with me here. All right. So first up, who signed off on the plans? When did they sign off on them? When did these signatures occur? Who recorded the drawings? And we get to the information of what's the page number, CD for civil drawings, And this is the demolition plan. So if I zoom in a little bit, they give us some notes: remove the existing drain line and remove the chain link fence. Okay, thanks. If I zoom in a little bit, I see this outline here. Same thing we saw on Google Earth. That's our rubble piles. Okay. Up here, it says that there's a rock outfall. And according to this, we have a 12-inch storm drain and an 18-inch storm drain dumping out right at that rock outfall. I see these contour lines that are showing me that I have a drainage swale. Okay. So this is how all this information ends up coming together. What are my existing conditions? What am I looking at? What am I building? Okay, how do we tie all of this back together? I'm bounded on two sides, three really, if you count the road. I've got a little bit of opening here, but you can't legally drain your property and dump everything onto somebody else's property unless that water flow was already going there to begin with. Okay.
And then there was a question in the chat from Mason. I'm just going to echo it. Are residential and industrial building codes the same annoyance in California?
Annoyance, those are the rules we have to obey to do the job. There really is safety in mind, keeping safety and protecting the environment. Those are absolute concerns. California can be pretty stringent, mostly because we're an earthquake zone. Mm-hmm. California tends to move a lot more than a lot of other states. So the soil conditions tend to play a bigger factor. The structural components tend to play a very large factor as well, just because of the nature of where we live and what happens to us. So, you know, areas where you've got strong winds or snow loads, those can impact regulations and requirements quite seriously. Mason, was there anything in specific you were looking for? Were you talking about the difference between residential and industrial, or just in general? Is it
just building and construction for residential? It's just annoying. I was just wondering for industrial builds. I don't know about you guys.
They're about the same.
Yeah, that's what I figured.
Yeah, pretty much the same requirements. Once you get onto private property, things change a little bit. Mm-hmm. But even on a site like this, even on a job like this, we were still under the regulations and requirements of Placer County, where we were doing the work. In the absence of any specifications provided by the architect or the civil engineer on the project, we would default back to Placer County specifications. So if our engineer didn't specify what kind of water pipe we were to use or the methodology of connecting those pieces, we would go back to the local specifications.
Yeah.
Whatever would supersede there.
Mm-hmm.
Architectural specifications tend to be vague but more stringent, I would say. You have to use this exact kind of rock and it has to have so many chip faces and blah, 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 and all these specifications. Mm-hmm. But the problem is whoever wrote that specification doesn't realize that you can't get that rock in California. It doesn't exist. So things like that, you really got to watch where you are. You can get totally lost in those kinds of details.
Oh, yeah. And I'm guessing Placer County is a little different than Santa Cruz County, too.
Around California, most agencies, most county jurisdictions, and down to the city level, most of the time they follow the Department of Transportation. They follow the Caltrans guidelines and specifications, and maybe have something specific based on where they are. Placer County is actually quite large.
Yeah.
Pretty rocky, pretty warm conditions. Santa Cruz, you've got the mountains, you've got fault lines. During earthquakes here in the Central Valley, we don't feel that often. So down closer to the fault lines, depending on where you are, you're going to feel something a lot stronger. So the specifications in Santa Cruz would address those conditions with more detail than Placer County would.
Yep.
So it can vary from county to county, but most of them stem from DOT work. That's pretty much the go-to. All right. So here we have more benchmark information. It's a 2.5-inch brass cap stamped Placo benchmark reserve 020 2012. Set at the top of curb, 5 feet south of wall at the northeast corner of Sunset Boulevard and the Highway 65 overcrossing. Not even on the site. So if I drag Google Earth back over here, here's Sunset Boulevard and here's Highway 65. Here's the site. So that's the closest benchmark. There's a note here. So if I hide that and zoom in up here, found 3/4 inch rebar capped RCE. Okay, RCE indicating civil engineer, that would be maybe a temporary benchmark that somebody had put in. Okay, so that's the demo plan. It's pointing out that we've got a rock outfall, we've got dump piles, we've got a drainage swale, but we saw that from Google Earth pretty much. All right, so we're on the same page there. We're not looking at anything totally different. This is the grading and drainage plan. So this is where engineers will marry up both the existing conditions and the proposed conditions. So what do we get from looking at those? So let me zoom in a little bit. Let's look at just the building pad for now, because there's a lot of stuff that's going on this sheet. It gives us an outline and we see little door symbols. Okay, so that's going to be our building. It gives us some call outs, these dark black call outs. Those are proposed elevations. Our existing elevations we see down here, they're very, very faint. And these were scanned documents, so, quality erodes over time. But here we see the outline of our spoil piles. We have a contour line of 135 right here down the middle. Notice how it connects back on itself. It doesn't cross any other lines. It follows all the parameters that we talked about earlier about what a topo line should have, what a contour line has. So here we've gone every 1 foot, 134, 133, 132. So we can assume that with this peak here and down here where it says it's the toe of the slope, just like your toe, down at the bottom at the edge where it meets the ground, we're saying that it's about a 132-foot elevation. Okay, so 135 down to 132, they're saying it's about a 3-foot stockpile. That's a yardstick over the course of this whole area. Let me just tell you, they were wrong. It was way bigger than what that was. But what we can see here is we can see that we've got a relative, other than these piles, 131, 75, 88, 74, 71. But this whole area is all at basically the same elevation, 131 feet. 0.5 through 0.88. So we've got 0.3 of a foot is what we're saying variance between, say, this point here and this point here. That's relatively flat. That's not a big steep slope. And we're saying that this is almost 120,000 square feet, even without having anything else to go off of. We know that that's pretty level ground, right? No major hills, but we can see here as the points converge, as we start getting a whole lot of data all on top of itself, that's what the computer has been plugging in, right? So it's recording all of that information, all those data points from the initial survey, and it's saying, hey, you got a hill here, you got a little bit of a mound. So we can get a lot of information off of this. It's a little hard to read. So usually what we'll do on the construction side is we will request the CAD files. So we're not drawing these by hand anymore. Used to have to do the volumes and the earthwork calculations by hand as well. But we will request those files so that we can lay them on top of each other, and we can let the computers do the difference. They can figure out whether I have to cut material out to get to my finished grade, or if I have to add material back in to get to my finished grade. So what we have here is, if we start looking at kind of one of these little corners here, what this is telling me is that right here at the building corners, we're at about 134 finished surface. So that's telling me that when I put down my aggregate foundation, and then I put down my concrete foundation with the rebar and the whole 9 yards, that we're expecting to get an elevation of 134.2. Well, if we're grading this, if we're moving the earthwork so that we can accommodate 6 inches of concrete slab, 8 inches of granular fill material that we can verify that it's compacted, and we've got really good material down there. So I have roughly 14 inches that I need to make sure we are below that finished surface, so that whoever's putting down that rock and that concrete can build that back up and hit that 134.2. So kind of really what we're doing is we're backing out those materials. We end up doing the same thing when we have asphalt paving. We have to back out whatever that material is to put our grade, our earthwork at that elevation. So that's what we need to do with this information, is we need to take our existing, compare the proposed, and figure out, what do we have to do with the earthwork that's here? What do we do with the material? So if that's the case, and once we get rid of these rubble piles, because they're not going to let us build on them, we don't know what it is, they've just got to go away. So if we say we're starting out at about 131.8 feet in elevation, I have a finished surface of 134.2, but let's say I have a full foot of material that needs to go on there. So in order to get to my pad grade, so there's finished surface and there's pad grade. Pad is the dirt level. What am I going to have to do earthwork wise to get to my pad grade, which is up here? Okay. So if I'm at 132 down here, I take off a foot from my finished surface, I'm at 133.2. I need to fill that 1.2 feet. That's a lot of material. Excuse me. Okay. But that's just in one spot. That's just right here. We need to look at the overall site. Where is the material coming from? Where is it going to? That's the key to earthwork and volumes. That's what the whole culmination is in all of this. Where am I draining my site? How am I going to use the topography of my existing site, the topography of my proposed site to make sure that I don't have ponds, puddles, unwanted ponds and puddles, the drainage. We already know that we're capturing drainage runoff from the property to the north. How do we handle that? How does that need to be mitigated? Okay. So we can get really a lot of information off of this one sheet. But bottom line, what we're looking for is we wanted, for our earthwork and for our volumes, we want to take our proposed grade, our original grade, and figure out where do they line up with one another. Ideally, if I have areas where my proposed is above my original, that's going to be a fill. I have to add material to get up to that new elevation. The flip side of that, if I have original and my proposed, then I have a cut. I've got to remove that material to get down to that proposed elevation, okay? In a perfect world, the amount of cut that I have on my site and the amount of fill that I have on my site would be relatively equal. And I have to say relatively equal because if you have ever dug a hole, you'll know that as you take the earthwork, the soil out of the ground, it expands. Okay. If you're trying to dig in really hard, really solid material, really dense material, once you open that up, you don't have the same volume. If you were to measure out your hole 2 feet by 2 feet by 2 feet deep, and then you measure the amount of dirt that just came out of there, well, let's see, that pile, that's about 3 feet by 3 feet by 1.5 feet. You're going to end up with different volumes. So the volume calculation really comes into play, and analysis of the existing conditions, the existing earthwork. What's the existing soil going to do? Does it have a tendency to shrink when we're done working with it? Does it have a tendency to expand when we start moving it? So the earth itself, the soil conditions, those really come into play, because it's wonderful when an engineer publishes, here's your earthwork quantities. You've got an 8-acre site, okay? Net cut, 5,370 cubic yards. Net fill, 6,297 cubic yards. Okay. So if I were to look at that immediately, the amount of material I have to take out of the ground, my cut, and put in my areas that are calling for fill, I need more fill. I don't have enough. If I just look at that, black and white, this piece of paper is telling me I need to bring in almost 1,000 yards more material to make my grades balance, okay? There is a list probably about this thick of different conditions that blow those numbers right out of the water. Okay, like I mentioned, soil conditions, moisture content makes a difference. What kind of material are we bringing in? What kind of material are we off-hauling? Is all of it going to be good material? What if I'm digging in a part of the area and part of the a corner of the site and I hit a pocket of mud? Somebody's got, you know, there's a buried structure there that's been holding water for 20 years, right? So all of a sudden, now my numbers are different. So that's the interesting thing. That's what we're going to be working towards in terms of cuts, fills. Why do we need topography? Why do we need to know what we have? Because we need to know what we want. We have to find a way to get it to what we want, okay? Anybody have any questions on this so far?
Well, I just had a question about just calculating all this stuff. I know there are computer programs, but I'd prefer to do it by hand first just to get a feel for what's going on.
I'm going to close my
what
mouth.
What would be a resource that I could use to go figure that out, or try stuff like that on my own?
Different ways of doing it by hand. This would be a difficult one to start with because of all the different appurtenances and all the things that are going on around here. There will be homework examples. This is just a very broad introduction to some of the terminology, some of the information that we're going to be going over. Just a basic intro that we've gone so far. Okay. Lots of different ways to go about calculating the volume that you're going to need. Computer programs are great. If you want something like this, you could take the perimeter of this building, divide it into a grid, right? And you can look at the elevation at the corners of each one of those intersections, figure out what your average elevation is, what your average difference between proposed grade and finished grade, an existing grade, sorry, between your proposed and your existing. And you could do that for little tiny squares by putting that into a grid format, okay? So if we were to do 10 by 10 grids, 10 by 10 horizontal and vertical cuts across here, and figure out what the elevation is existing, what the elevation is proposed, take the difference, we'd know whether we've got cut or fill on that building pad. It is an extremely long and tedious process.
Yeah.
Especially when you get out into the other areas. Roadways, where you have more consistent sections. So here, everything changes. Anytime you turn, things change. If you have a roadway, you've got a long, straight, linear, not necessarily straight, but you definitely have a much more linear project that you would be looking at. There you would probably end up looking at cross sections. So instead of taking a square and saying, okay, I have this chunk of cake, right? I've got so much cake, I've got so much frosting. Those are my sections. What cross sections will do is that they will run a line across an entire area, which is really easy when you've got a roadway. So you go from the left-hand side of the road to the right-hand side of the road. And when you have your boundaries like that, you might have a swale coming down on either side, coming back up. You've got a little bit of a shoulder, and then you have your roadway in the middle. So you can take that typical cross section and plot that against what's the typical profile of the ground doing currently. So let's take, let me see if I can come up with one that's pretty good. Let's take Soquel Drive right in front of the school, okay? So if you are looking, let's say we're looking north, right? To my left, it typically drops down towards the athletic fields, right? The school itself is up there on a hill. You've definitely got a rise. So your cross section, your existing cross section would do something like that, right? Kind of a little, I don't know, what would that shape be, right? A lazy S, okay? So you'd have something along those lines. And if you wanted to build an extension of that roadway, say you wanted to add another lane on the west side of that area, what would we have to do? Well, we have an existing road, we have an existing slope down to the athletic fields. If I want to extend this out, I'm going to have to fill that area here. Now, if I take a whole bunch of cross sections, I can average out what those areas are. So then if I have this situation, right, where my existing roadway is my forearm, my hand is my new section, my left arm is the existing ground, I can take from my proposed, draw a cross section and figure out what that area is, right? And say that for 20 feet, it's going to be like this. But then the ground changes at that point. So maybe for the next 100 feet, it's going to be this kind of a slope. So a much smaller area here. So that's another way we can go about doing it. Those are all topics that we will end up covering next week. Still trying to get our guest speaker to focus and show up. So he's going to talk about projects that he's done. He's done a lot of work with levees and the infrastructure. So cross sections are a big thing that he and his business do. Definitely something we can talk about in terms of volume. How does he design that? And how does he look at the volumes? One other guest speaker that I'm hoping to bring in, and we might just double up next week, is one of the guys that I work with. His sole purpose, his sole job is to do the volumes and the earthwork and the takeoff calculations. So he would take that CAD file, manipulate it into AgTech software as one of the products, and generate the cut fill maps. So I'll see if he still has those, if he can get those open for this particular job, so we can look at that and you can see what it would look like in terms of a cut fill map, color coding, shading, that sort of thing. So we know how to read and interpret what is it that we're building. Okay. So it's 9:02. Does anybody have any questions? All right. So one more thing I wanted to show you real quick. Let me zoom back in here. Oops, wrong way. So just for grins, you can kind of see how this tapers off here. You can tell it's been graded, it's been mowed by the stripes in it and the striations. But if we advance through time just a little bit, that's when we started the job, August 2013. So you can see that we've gone out, we've got some heavy equipment on the site. The pile seems to be pretty much gone. We still have some drainage here. We've improved this area. We've put a fence in around the site. So Google Earth can be kind of fun when you're looking at projects like this and how they progress. 2014, we've got a building up. It looks like it's a mess. We've got construction traffic all over the place. We've even built out a parking lot out here because there just simply isn't room for all the employees, all the equipment, all the materials. The logistics on this were just a nightmare. So we ended up building them out a 2-acre parking lot just so they had some extra space.
Wow, that's funny because looking at the plans, you can see originally they had a staging area that was kind of tiny. And then
yeah, they assumed this was going to be sufficient. These are all the job trailers. Not allowed to cross over onto the existing property. And they thought they were going to put some more parking and, oh, our people will just park there. This job had such a hectic schedule. It was such a fast track job that you had the HVAC, the electricians, the plumbers, you had so many trades, the building trades, the drywall, all stacked on top of each other, all trying to work all at once. And we have our big equipment. Let's see if I still have it open. I guess I don't. Bummer. Must have closed it. So when we have all of our huge equipment out there with human beings standing next to it, they end up looking a little bit small. So there's one of our guys, and this is a small scraper. This is a small piece of equipment relative to what we usually have. And I can tell you that when there is a stream of hundreds of people every day walking across the path for those kinds of pieces of equipment, you are asking for trouble. So safety is another big consideration that we have to look at and how you build out a job. So, yeah, fun stuff. I'm gonna go have nightmares now. You guys all go have pleasant dreams. All right, so with that, exam 2, the rework, due Wednesday by the end of office hours. Homework number 7, the one that I forgot to post, I gave you until Friday at 5. So get that in by Friday, 5 p.m. Again, it is seriously 5 questions on scales. Most of it is math we can do in our head. So if you have any questions on that, do not hesitate to reach out. Homework 8, topography, that's due next Monday by the start of class. Reading assignments, chapters 14 and 20. They're both very short chapters. They'll go pretty quickly. Next class, next Monday, November 9th. Yeah, topography is due November 9th. No, today is the 9th. All right, next class. Next class is not November 9th. Next class is November 16th. All right, we'll continue talking about earthwork and volumes, and hopefully my guest speakers will stop being flakes. And we'll get them in so that you can hear somebody else's voice for a change. Reminder, office hours are Wednesday, 12:30 to 2:30. Most of the time, I just sit there and do my other work, or I surf Facebook. So please stop in, say hi, get some help. Message me if you got any questions, if you need anything. If not, stay safe, make good choices. Stay warm. It's autumn now.
No, okay. Thank you. It's been really cold up here, so.
All right, well, we went from having the AC running to running the heater in the course of about a week and a half at my house, so. All right.
Well, thank you. I really appreciate it. I got most of my questions answered for the most part.
Yay.
So I'll definitely, I'll see if I can go to office hours and ask a few more, but that was really helpful. It gave me a little more insight.
That's what I'm there for.
Yep.
Okay.
So thank you.
Cool.
I appreciate it.
You're welcome. Have a good evening. All right. Stopping the recording.